Well, good morning, everybody. Could be afternoon, could be evening. It's a pleasure to join everybody today. Thank you, Matt, for that great presentation. We're going to switch gears a little bit here and go into some low-level stuff. So hopefully, it's not too early for anyone. So first, it's a pleasure to be here. Excuse me. My name is Seth Berman. I'm the president and CEO of Instantiations, and joined with me today is Alexander Mitin, who's one of our senior software engineers, but he's also the virtual machine team lead. So if there's anything I can't answer, well, he's definitely the one that can answer the questions. So first, who is this event for? Well, it's Developer Month after all, so this is geared very much towards developers. We'll try to keep things at a higher level where possible, but because time is limited in the session, we're sort of holding all Q&A until the end. But if you if you forget your question, feel free to put it in the chat window, and we'll answer it when the time comes. So a little bit about the agenda for today. First, we'd like to just briefly introduce ourselves and talk a little bit about who we are and what it is that we do. Then we're going to launch into sort of an overview on just-in-time compiler technology, sort of dynamic translation, and especially in the context of IoT. So I'll be showing you some benchmarks with sort of an emphasis on the trade-offs between speed, sort of memory, power usage, the last two being, far more important in the IoT context and cloud space as well than sort of your traditional big servers and desktops. I'll be demoing some of our tools and benchmarks that we use. We're going to be doing those. The benchmarks are run on an ARM-based Raspberry Pi 4 using our VAST platform. Finally, we'll have a Q&A session at the end where you will have an opportunity to ask some questions via the chat window if you'd like. Okay, so who are we? Instantiations. First of all, a big long name. But being around for about 30 years, we have a really rich history, as you might imagine. Within that time, we've had various mergers and spinoffs and acquisitions that have occurred, but fundamentally, it's been the same company through the continuity of its founders, the business focus, our name, since it was founded in 1988 in Portland, Oregon, although we're presently headquartered in Raleigh, North Carolina. We sort of hit our stride in the 90s with a focus on Smalltalk and Java solutions, where we forged relationships with various companies like IBM. And during this time, we became a founding member of the Eclipse Consortium, which later became the Eclipse Foundation. Sort of as a result, we were one of the first IBM partners to be briefed on the Eclipse IDE in 1999. So due to this strong relationship we formed with IBM over the years, in 2005, we reached an agreement with them to assume support and development for their Visual Age for Smalltalk product, which is now named the VAST platform. So some of you may remember the Visual Age suite of products back in the day. So in 2010, Google acquired our Java products. And at that point, our focus shifted solely to the design and development of the VAST platform. So presently, we are working on continuously improving that and expanding into new areas like IoT and other types of custom software development and consulting. So just to be clear, while we have expertise, and a lot of it in Smalltalk and Java, the skills needed to build these platforms and tools sort of require significant expertise with assembly, C and C++. We have a lot of experience with languages like Python, Dart, and Rust internal to our team. So if that need arises, we're very familiar with those. But our primary product, as we mentioned, is the VAST platform. And so while we're going to talk about other languages today too, this will give you some context when you hear VAST come up, because I'll just start calling it that for short. So VAST, it's an advanced software development platform with its earliest version originating all the way back from 1993 as Visual Age for Smalltalk, for those that may remember. And since then, we've had at least a yearly major release, and it's, a 2 million line code-based product at this point. It runs natively on Windows and Linux with Intel-based architectures, but an official release for ARM32 and ARM64, Linux is coming in the next few months. And it's well suited for, edge devices and cloud-based servers. So VAST is, highly scalable. It's very productive due to our augmentation of the platform over the years. and due to it being Smalltalk based under the hood. So it's surprisingly productive. In fact, we've just heard recently from a customer that when two teams were building the equivalent systems in BAST and Java, it took 2 months to build it in BAST and 9 months for another team to build it in Java. And I hear these things and the skeptic in me asks, well, what was the expertise of the Java team? But stories like these aren't uncommon for us to hear. I've been working with Smalltalk since about 2001. Within that time, a professional Java developer for about 4 years. And I worked with Alexander's VM team for 5 years to help rewrite IBM's Smalltalk virtual machine. And I love my experience with all these languages. I'm just sort of a technologist at heart. But I will say nothing beats the productivity of a live programming environment like Smalltalk. It just doesn't. So I concluded, this is a very reasonable statistic that I heard. And for those that haven't heard of Smalltalk, it was one of the first object-oriented languages, has pioneered many concepts in modern software development. Concepts like the IDE itself, the model view controller paradigm, code refactoring, graphical user interfaces, the list goes on. VAST is currently used by Fortune 100 and 500 companies, numerous small and medium-sized businesses, as well as independent developers in various domains like finance, insurance, healthcare, to agriculture and facility automation, just to name a few. And to relate things back to our session today, though, the Smalltalk language is a pioneer in just-in-time compiler technology. So Dart, JavaScript, and Java virtual machines all have roots in Smalltalk and Smalltalk Lite technology. In fact, the language design community is a relatively small group of people, relatively speaking, and many of the designers of Dart, of JavaScript V8, and Java were Smalltalk virtual machine and language designers at some point. So let's get to it. Let's talk about just-in-time compilers. First, little definition. In case for those that may not know, a just-in-time compiler, we're talking about compiling machine code at runtime as opposed to compiling it ahead of time. So this will result in programs that can run at much faster speeds than they could otherwise if they were interpreted. And the point? Well, the goal is to make higher level languages begin to approach the speed of lower level languages like C. Faster is better in most cases, but sometimes the fastest option is not the best when considering sort of the big picture in software development. And we'll talk more about this later. In fact, if you stick around for the next session, you'll see, the live programming environment, as Mariano will show, the debugging experiences in languages like Smalltalk. Now, there are some situations where native machine code generated at runtime can actually produce faster code than what ahead of time compilation could provide. And the reason is you have the opportunity to profile guide at runtime and rewrite new, more optimized code for specific cases. You can also, set it up so that you can observe the CPU extensions that are running right now on the hardware and maybe take advantage of that with code that you generate. And that's easier to do than with ahead of time compilation. So how are JITs faster than interpreters? Well, every programming language has some overhead associated with it. In this context will be, overhead is the additional code threaded throughout your program, which can be removed or optimized. And the removal or optimization of this overhead is what JITs do that make them so much faster, make the code run faster. So how do we do it? Well, there's a lot of techniques and classifications for JITs. So what we're showing here, and they're not exclusive from each other. What we're showing you here are strategies, implementation techniques, and basic classifications. And some of them work well together. The first kind, and this is probably the most prevalent, is the method or function-based just-in-time compiler. And this is about boundaries. What is it going to be producing native machine code on? And in this case, it sort of looks at the method or function scope and optimizes machine code at that level. So what are some advantages of doing this? Well, it's a well-known boundary. Pretty much the runtime systems are already geared towards running or executing methods. So it's kind of known where you're going to start and stop this endeavor. It can also have faster compilation than tracing can. Disadvantages? Well, in most, but not all cases, and we'll show you the not all part, but in most cases, you need a compiler in memory, which is going to increase the runtime footprint your runtime, sometimes substantially. Another disadvantage is there's typically less optimization opportunity than tracing, because tracing can build a larger picture than just what's at a sort of method or function boundary. And so there's lots of examples of method or function JITs. I mean, that's what we have, say Java, and a lot of other systems as well. This is not just about, just-in-time compilers, but it is a strategy that is used, especially in dynamic languages, to help make them a lot faster. And it's the concept of profile guiding. And you can do this with static compiler pipelines as well. But in the context of at runtime, we can profile and do things like detect hotspots, which is code that is running a lot. And we can generate new, faster code for those hotspots. But there's other kinds of things that we might be able to do. We might be able to prove that certain checks are no longer necessary, and we can remove those at runtime. So the just-in-time compiler is always kind of looking for those opportunities, and that's really what profile guided means. So advantages are, you can rewrite the code at runtime for that specific situation to produce really fast and optimized code. Disadvantages? Well, if you're going to profile, you're adding profile overhead somewhere. And so that's often more code, but it's also time. You have to invest that time, which hopefully pays off later. Lots of examples. I mean, I would say it's used in pretty much any virtual machine. There's some level of profile guidedness in it typically. Okay, so a lot are method-based JITs, but there's also these sort of tracing-based JITs. And that is the idea that, so it's a form of profile guiding where you basically are looking for traces or hot paths of code that are executing all the time. Generally, it has a profiling stage. Typically, in this context, it would be the interpreter itself, the language interpreter that's actually keeping track of and trying to build a trace or path from which it decides that this is a good path to generate native code on. So some advantages are it's very efficient code for hotspots. And another one is you can typically have it be more memory efficient than a method or function JIT. In other words, a method, you'll be generating native machine code at a method boundary, but perhaps the hotspot is just a single loop that's inside a big body of code. And it's not free when you generate native machine code at runtime, you've got to put that somewhere. And it's often bigger code than your intermediate code is. And so that has to be stored off, and that takes memory. And so if you're always doing it at the method boundary, you're often going to have much larger sections of memory than what maybe tracing could offer you. But it sort of depends on the profile of your execution. Some disadvantages, well, you'll definitely need a compiler at runtime. It's going to increase the size of your runtime. And it's going to add profiling overhead. I mean, you have to be able to detect these traces, and they're not necessarily on nice known boundaries like methods. So you're going to need some sort of compiler that's able to take that path and generate the native machine code from it. So used in a lot of multi-tier JITs, as well as PyPy, for example, is a tracing JIT built on top, or basically on top of the Python language. And finally, we get to the template-based JITs. And so these are most interesting to us because this is what the VAST platform uses. So template JITs are an implementation strategy for method or function-based JITs. And so, like I said, it's the one we have. And templates are the native code equivalents of the instructions like bytecodes and call return machinery of the virtual machine itself. So we prepare those ahead of time when we're building the virtual machine, and we store those results off in an object file. So when it becomes necessary to convert a method to native machine code at runtime, we take copies of those associated bytecode templates, wire them together, do some post-processing, such as filling in certain placeholders now that we know actual memory addresses, and we do some light optimization passes. In the end, we're not going to radically change the native machine code from what the templates would describe, But we do have some peephole optimizations, such as removing unnecessary push pop instructions and things of this nature. So the advantages, well, it's very fast to, quote, compile. It's not really compiling at all. We did that back at build time. It's really assembling it and linking it into the running program. So very low overhead, and it doesn't have to include a compiler in memory. So you only sort of need this linker-like part. The disadvantages is it's going to be less efficient code than an optimizing compiler. I mean, that's absolutely true. But it still buys you a lot because you get to remove the interpretation overhead, which will show you the cost of that in a moment, and several other optimizations that helps give you that 2x, 3x, 4x speedups that we're looking for. And this is what we use in the VAST platform. Okay, so what are the tricks of the trade when using these techniques? Well, the first thing we want to do is we want to remove the interpreter and the interpreter overhead. Now, for many people typically know that interpreters are slower. I mean, but maybe not why, or just how much overhead we are talking about whenever we use an interpreter, even the best and fastest interpreter, ours is one of those. So here we have, what I'm showing here are ARM32 instructions for a single bytecode in the VAST platform. The only thing this bytecode does is it's basically push a class variable on the program stack. That's all we really want to do here in preparation to return it from a method, from an accessor. Okay, so let's look at this machine code a little bit, and we don't have to look at the instructions so much themselves unless you want to, but really just pointing out the overhead involved. Because remember, what we're doing here is we're essentially emulating a physical machine. And so all the things that are wired in hardware that makes machines run are things that we're emulating with data structures and things that we do in programming languages. And so the first thing we see here is the bytecode decoding overhead. That's going to chew up 3 instructions in this case. The next thing we see is the bytecode dispatching overhead. The only thing this is about is how to get to the next instruction and increment your program counter. That's it. But you can see here, and even though the compiler was nice enough to reorder 2 of the instructions on 4 and 5, it's basically a lot of instructions to just go to the next bytecode. And so all that is overhead. And so at the end of the day, the only real work done in this bytecode is lines 6 and 7, a load and a store. So now what our JIT compiler does is basically when it wires together the native templates, all that is removed. And what we see here is a calculated load and a store. And that's kind of what we want to get it down to. And so every interpreter has this overhead. And in fact, many that are written in C and maybe use switch statements and things like this are going to be much slower. There's actually going to be a lot more overhead and worse branch prediction and these kinds of things. So ours is actually a very fast interpreter as far as interpreters go. But still, you can see even a basic JIT should be able to give you at least the 2x, which is what 2x speedups, which is what removing this overhead typically buys you. Okay, next, this is sort of a broader methodology, but we want to optimize the executable code, not unlike what a static compiler pipeline would try to do. Except, of course, we're at runtime and time counts. So we don't want to spend a whole bunch of time trying to optimize, certain code paths to the nth degree when they may change and it may not have been worth it. But we do want to do some basic things. And there's many examples of what we could do. It's all just time, really. But one of the most common things, and the name of the game, is inlining. How do we basically, here's an example at the bottom where, we have a call to a function. So there's that call overhead. There's, and now you're jumping away somewhere else. So the optimizer for the, is not able to optimize the registers as well. And instead, if the compiler can say, oh, well, that's a really small function, it's really just makes sense to kind of take the body of that function and snack it right in place instead of calling out to that function and incurring that cost. Well, that's what inlining is, at least in the context of calling a method or function. There's actually other forms of it as well. Okay, now we're going to look at the machinery for calling methods in sort of dynamic late-bound languages like JavaScript, Python, Smalltalk. So here, at a particular call site, which is sort of a receiver being requested to execute a method, x.toString, the type of the receiver isn't known in these late-bound languages, in a dynamic language. And so we have to ask. And once we have that information, we have to perform a lookup to find the address of the method body or the handler to go to. So in languages like Smalltalk, with inheritance, this means asking each class and then its superclasses all the way up, do you have this method? Let's say we're looking at toString or asString in Smalltalk. You first, in this example here, X maybe we asked and it was a string. And then we say, but maybe toString is defined an object or asString. And so we're asking the question, well, do you define this in string? No. Let's go up to arrayed collection. Do you define this? No. Let's go up to sequence. You can imagine this machinery that has to take place to resolve these lookups is extremely expensive when compared to, say, what might happen when you compile a function call in C, which is basically a branch to an address, right? So it can be quite expensive. And so imagine, as we said, you have to perform this for every message send or method function call, and in a dynamic language like Smalltalk, there's a lot of these sort of geared towards that. So it was noted at some point that we could perform the lookup one time and then cache the result sort of in this global table that everyone shared. And this is called your first level lookup cache. And that's what you see in green there, where we do it once and then we sort of store it off in a cache, the address for the next time. But there has to be a key, and that key is the hash value of typically both the receiver and the method name sort of, could be XORed or whatever the case may be. That becomes the key into the table. And so there could be collisions, and you'll have to handle that. It's a global table, so not great for branch predictions, since each call site would end up going there. It's much, much faster, but still, the question comes up, well, now that we have sort of this engine that can rewrite generated machine code at runtime, can we do any better? And the answer is, yeah, we can. So now let's move on to a further optimization technique. And like I said, this really requires the ability to rewrite generated machine code at runtime. So this is called inline caching. So we're going to take the concept of what we just talked about, the first level lookup cache, and we're going to see how to localize it sort of at each call site, sort of inline it at the call site itself, and tailor it just for each call site's specific situation. So we want to get to the branch predictors working for us, and we want to transfer control to the method body as quickly as possible while still being technically correct. So these three states, monomorphic, polymorphic, and megamorphic, they're basically the three states, other than an uninitialized state, they're basically the three for an inline cache, to capture and use to its advantage what was noticed about the behavior of typical programs in these dynamic runtimes. And so what was noticed is that most call sites that are active in the program only really ever have one receiver. I mean, yeah, they technically can have n number, but for most programs, the general behavior is it has one. Or it can have a few, or it has many. So there's not sort of this uniform distribution of types. You either have one, and then next maybe you have a few, or you just have a bunch. Okay, so a monomorphic call site, the call to the lookup method routine itself at the call site is rewritten at runtime with a jump to the cached address of the method itself. Well, almost. Remember, this is a dynamic language, right? So the receiver type might have changed. So how do you know that if you're going to hardwire it to go to the method body, how do you know you still have the right method? Maybe a different receiver came in. Okay, so it could be the case that it's now different. So instead we jump to a section just before the method body called the preamble, where a simple check is performed on the type. And so if it's still the same type, then it may proceed to the method body. If not, well, it'll perform a different strategy. This could be returning to that expensive lookup procedure I told you about before, or it could be to build what we'll talk about next, which is a polymorphic inline cache, which I'll abbreviate that big long series of words to PIC. That's generally what it's called. So PICs are similar to the lookup cache, except that it performs sort of a linear search just by checking the types for each slot. And if it matches, then it jumps to the address associated with that slot. Okay, so and if not, it'll go to the next type and then check if that's the type, the receiver type is correct, and then it'll jump to that address. Okay, so we in the VAST platform use a 4-slot PIC. So finally, consider the situation where a piece of code loops through all objects in the system and calls, toString or asString on it. So you can imagine that call site there is going to have an incredible number of types, and the bookkeeping behind keeping the inline caches updated for that situation is going to be more overhead than it's worth. So in this case, the inline cache transitions to the megamorphic state, where it will basically perform the normal lookup routine in a slightly more optimized way. Okay, now we've had that sort of flyby of just-in-time compilers, as well as sort of considerations, dynamic translation in dynamic runtimes. What should you consider when choosing JIT language for IoT and edge computing? Okay. Well, balance here is important. When you rank just-in-time compilers, and we hear people talk about them, they're often, considered in terms of performance first, and then sort of memory. You hear the my JIT is better than your JIT, means that, you hear it in terms of mine's 2x, 5x, 10x, 20x, 50x speedups, okay? Then at some point you may talk about memory because there is a substantial footprint often. And then, so basically, and as well as you have a native code cache, you have a piece in your system that's running where you actually have to put this dynamically generated code. So it has to go somewhere, and that takes up memory. But there's not a lot of scrutiny. I mean, there's some literature on it, but there's not a lot of scrutiny given to some of the other criteria that we might consider in the IoT context, or even cloud context, such as power usage, those kinds of things, energy usage. So we're going to look at some benchmarks here, and they're going to be of some different languages. And what we're trying to show here, essentially, we're going to use some of the benchmarks from the language shootout online. Now, this is really difficult to do. I didn't want this to turn into some sort of language war, so I chose different benchmarks for each language. And the reality is, if you go look at the language shootout, benchmarks for a particular language, there'll probably be like 7 different versions, even for the same benchmark, because somebody's, taking advantage of some piece of the, of the system to get the benchmark to run faster. We're really not interested in showing, the raw speed compared between languages. We're more interested in seeing the payoff of a JIT, and really these will show the payoff of a JIT on its best day. It will be worth noting the payoff of a JIT on its worst day. So these all allow the JITs to put their best foot forward, and we'll just kind of look at it from an energy perspective and as well as a memory footprint perspective. And a lot of this is intuitive, I think, when it comes down to it, but it's still sort of interesting to see. Okay, so here's Python. And so what we have is sort of the canonical version of Python, which is the C Python interpreter. And it's followed by PyPy, which is a tracing JIT. For Python. Now, this is actually faster, what we're showing here. We ran the in-body benchmark with the value parameter there, which I'm going to guess, I can't even read, the 5 million maybe. And so, what we're seeing here is an incredible speed up for the JIT if we look at the first one. And I think it's even faster than what they typically claim. And when I've run some other PyPy examples, I am seeing what they claim, more of a 6x, 7x type of speed up. See here, it's far more than that. And quite frankly, it's as I said, we're allowing everybody to put their best foot forward here. We're providing a fairly small piece of code that's doing the same thing over and over and over again, and the situation never changes. And so the JIT does quite nicely in this. However, let's look at the memory footprint. Well, there is quite a memory footprint here. And in fact, even on program startup, PyPy is almost at that level. It's not really the native code that's produced afterwards. It's all the engines and everything that's in it. We can see that compared to CPython, whose interpreter runs with about a 7.1 megabyte, resident set throughout, and it really is doing the same thing all the time. So there's not a lot of, adjustments of the resident set size for these guys. It pretty much stays the same. So we see that's quite a difference in memory. But if we look at energy, and by the way, I'll just hold up the box real quick. If you guys can see, this is what we kind of used to measure energy output. This is the Hobo plug load logger. So we basically plugged a Raspberry Pi 4, which all these benchmarks are running on, into this guy. And then we actually logged the energy output from these, and specifically here in milliwatt hours, to just get a sense of, usage. And so what became evident later is what we see here, is that you see sort of the energy is proportional to the speed up. Now, that's not always true. I mean, if your method of speeding something up is to add more processors to the mix, well, now you have processor switch overhead and several other things that will not make that necessarily linear with respect to increasing the number of processors. And even in the JIT case, and this is what I want to point out, it's not true either. Like I said, we allowed everybody to put their best foot forward. What if we what if we ran something where it was forcing the JIT to always have to rewrite the code because we made the situation change all the time? Well, you could expect a substantially different picture. The energy would increase substantially for the JIT because it would have to be running and generating that code. Now let's look at Java. So Java, and we looked at the OpenJDK. We couldn't really remove the JIT when we ran the interpreter, and that's kind of like ours. I mean, it still came with the runtime, so it was still part of the memory picture, but it lacks some of the JIT data structures and the native code cache, the native code that was generated for this particular run. So we ran Mandelbrot with that parameter, and we can see, yeah, it had an incredible speed up, as one would hope. And basically we see that, already the baseline interpreter is quite a footprint there. But it only increased a little, with this small benchmark with the JIT. And like we've been seeing, and like we will see, the energy usage is proportional to the speed up. And it's sort of, again, it's becoming clear why this might be. We're choosing benchmarks that peg the CPU. There's not much for the JIT to do after it generates that native code the first time. And then after that, you're dealing with a single sort of logical instruction stream. On one hand, in an interpreter, you have the overhead come with it. And on the JIT side, you're removing the overhead, but you're still doing the same thing. And so we kind of should sort of expect this proportionality. Okay, finally, we'll move to the VAST platform. And so what we are getting is what we would expect to see. It's a little better than 2x, but I would expect to see 2x. So we ran the FASTA benchmark with that parameter. So the only thing that is sort of artificial here a little bit is the memory. It still looks like it has a pretty big memory footprint. It doesn't increase a whole lot with the JIT. The reality is that our baseline interpreter without the, so we have built our virtual machine using the LLVM compiler toolchain, and it generates the native code for us. There's actually at runtime, there's only one piece that we need from it that we're going to switch out, and that is the part that reads the object file, the native templates from the object file. Well, so unfortunately, the GNU linker, unlike our Clang linker, is not as good at removing all those parts. So what we really have is about a 700K virtual machine, but it has all those pieces that got dragged in just so we can read the object file. So we're going to be correcting that, sort of probably doing our own object file reader so we can get back down to the 700K plus that code for the object file reading. But this is the situation as it is now, so fair game. This is what it is. So the energy usage again is proportional. But the situation here to bring up is, you know, we should expect that ours is always going to be between 2 and 5x. There's not going to be a lot of variance because we don't have an optimizing compiler in memory. For the other guys, you can create all sorts of situations to make it, you know, the 25x, or you could make it slower. You know, it's a lot of variance there. We're not going to get a lot of variance with ours. It's going to be very kind of steady. So this makes for a good first tier JIT. There's also, you can add on later an optimizing compiler, which we may do, but it will increase the footprint substantially. Okay, so now I'm going to quickly introduce the platform itself. Since, you know, basically we're gonna look a little bit on the Raspberry Pi. I'm going to run sort of the benchmark that you can kind of see. We're going to talk about sort of the runtime image size. We're going to compare them to, you know, we're just going to take a look at it and see what's up. Okay, so let me bring this down. I'm going to bring up the Raspberry Pi interface here. Let's see, get this guy going. Okay. All right, so here we are. And sorry, my head has now got to look at my my other screen here. I'm not going to be able to type and look at you at the same time. So the first thing I want to show is, so here we have what we've been running is our benchmarks, and it's represented as this ICX file, which we'll take a look at here. So our ICX file, I mean, if you're familiar with you know, Java, let's say, I guess you could sort of categorize it as the concatenation of all the .class files and sort of the runtime needed to, you know, in the Java language needed to run it, like the jar file or something like that. Well, this is roughly on that level. So we have ours down to about 592K for these benchmarks. And in fact, what I constructed was a program that included a whole bunch of benchmarks. Just to give you an idea of our development environment size, when you launch the VAST platform in the development environment, you also are launching one of these image files, but it's going to be something more around 12 megabytes. So what we essentially have to do is figure out, because that comes with developer tooling and all these kinds of things, and we basically have to figure out, you know, how to strip that down to just the program that we want. Well, traditionally, you know, there were a lot in Smalltalk, you use these image reduction tools that basically try to figure out what parts of the program of those images not really needed and try to get you down that way. We do offer that. We also have another methodology that allows us to build up from the bottom with sort of these coarse-grained pieces. And then from that, we perform reduction. And that's why we can get down to the very small, relatively speaking, a pretty small amount. So just showing you how we might run this here. So I'll just do, well, I was going to run the whole benchmark, which I probably don't want to do. So first, let me just, okay, so in this we have, you know, thread ring, Mandelbrot, some names I can't pronounce, pi digits, FASTA, in-body, binary trees. So the one that we ran was FASTA, which I'll just kind of run here. I'll do a smaller value parameter just because there's no need to sit here while you watch it wait. So now we're doing it with the just-in-time compiler. So that's, you know, 2.6, 2.7 milliseconds. Now what I'll do is I'll disable with the -mcd, I'll basically disable the just-in-time compiler for this one. And what we should probably see is around 2x, so I would suspect what, 5 and change, yeah, so 5.7 milliseconds without the just-in-time compiler. And so now we might want to know, like, what are some of the tools that we use to actually look at these things? I mean, sometimes I get reports in that kind of go like this. You know, I ran this single line of code, and as a result, your, you know, VAST platform virtual machine is twice as slow than it used to be. So, you know, there's thousands of different ways to look at the virtual machine performance. Doing one line never really gets you there. So basically what I usually do is I say, okay, well, let's see what's involved in that one line. So now for FASTA, for example, so we run at some speed. Well, that's fine, but what is it doing? And not just at the sort of statement expression level. I mean, so here's the one we used for Python. You know, and so we can sort of see from an expression or statement level what it's doing. Here's the one that we did for, you know, for Java. We can sort of, again, see what it's doing at the statement expression level. But I kind of want to know what parts of the virtual machine is it actually exercising? So what I'm going to do is I'm going to actually launch VA Smalltalk with call grind activated, which is sort of this part of the Valgrind suite, and it will track instructions. It'll simulate a cache so we can get caching behavior and a few things like this. So here's the development environment, and we're going to basically at this statement where I'm calling, okay, at this point, turn on the instruction, basically capture the instructions at this point. And then I'm going to run FASTA, and I'm going to do it for a low iteration count just because we don't care about time per se. We just want to know, you know, what's involved with it. And then it'll flip it off. So we'll absorb some sort of instructions for flipping it off, but that doesn't, it just becomes noise. We don't really care. Let me go ahead and execute this. So this won't take very long. Now it's done. I'll close it. It comes down, and now we have these series of call grind files, which I'll use a visualizer on. I'm kind of a visual person, so I like to have these. Some of our other guys like Alexander, they don't need these things as much. They just do their thing in a different way, better way probably. But I like using these tools. It just helps me to get a more of a broad sense of things. So in our interpreter, and we model everything as a function. So even bytecodes are function, they're tail call optimized function calls. So basically I can start to see everything with BC that you're seeing here is a bytecode. That's the bytecode handler. And here's the instructions. We don't have any source because this is, we generate the interpreter from the LLVM API. We don't actually write this. The interpreter does not run on a C runtime or something like that. So we just sort of have the machine code to look at. So we can, and if I want to look at all the bytecodes that are involved, I can just sort by the function name and kind of see all the bytecodes that we're talking about. And I can look at sort of instruction density. I can, because it's simulating a cache, I can get an idea of, you know, the read and write, you know, misses behavior for that particular cache simulation. I can look here at the, you know, how it's behaving. Maybe something, there's been a few times where we just didn't have the, you know, the pad, we didn't have things set up correctly for, and it just was jumping all the time. And if we gave it different hints, it would produce more inline code in the common case. And so these are the kind of tools I use to kind of look and say, okay, well, let me get a general sense of, you know, sort of what's going on with this benchmark. And so for, you know, I see basically to my eyes, I mean, I see a kind of loop here. This is a special inlined bytecode that does a big giant loop. And basically I'm seeing, you know, there's some float stuff going on. After we get just the basic engine stuff out of the way, I see some float operations. And so we can look at the float primitives and see if, you know, everything is running okay. And the nice thing about the way that we've developed our engine is that we have sort of a single code base that gets, when we're building the virtual machine, it gets run 3 times. The first time it generates the interpreter. The second time it generates a special debug interpreter that we use in the live programming environment. The third time it generates the native templates, what we use to link in for the JIT. And so what's nice about that is typically if there's a problem in one, there's a problem in all. So, and if we fix it in one, we fix it everywhere. There's only been a few times where, you know, we upgraded the LLVM code generator and there was something very specific to what it was doing. But even then we're able to find and spot these bugs fast. So like I said, I mean, it makes a very good first tier JIT. It does what we want it to do. It gives us that 2 to 5x that we're looking for. And and this is a little bit, you know, at least this is my version of how I like to look at things down low, how we can fix problems, how we can, you know, analyze performance down at the VM level instead of sort of up high at the instruction level. Okay, so I'll get back to the, we're about done here. I'm just gonna finish up with the presentation. I'm going to swap here, and I was trying to find a good way to get back to exactly where I was, but I'm pretty technical, but for whatever reason, I'm horrible with PowerPoint. Okay, so before we get to the Q&A, just want to give a quick summary. If increasing performance while maintaining a good balance of energy usage and development productivity is sort of a goal of yours, the VAST platform could be a really great place to start. But we understand many factors go into choosing your development language and tooling, like sort of available libraries, time constraints, performance and hardware needs, deadlines, team experience, just to name a few. So that said, regardless of the different technologies our customers have used over the years, we've been there to help them solve their most difficult problems during the software development cycle. And with that, Alexander and I are both available for Q&A. So if you have any specific questions on how the JIT design was approached or how we overcame certain issues, we'll be happy to share those with you with any remaining time. And while I'm familiar with the JIT, as I said, Alexander is sort of the lead architect and implementer of the magic, and so he's happy to answer, the more involved questions that I might not be able to answer. And of course, you can always reach out to us. There's our contact information, and we're always happy to talk. So thank you.
Thank you so much, Seth. Great presentation. If anyone has any questions, please do put them in the chat box, or you're welcome to unmute yourself and ask a question. We'll give it a couple minutes, see if people will wake up. They seem a little quiet today. Here's a couple questions. Seth, first one, is the JIT compiler platform independent?
Yeah, that's a really good question. So I'll let Alexander take this one. Actually, it's interesting.
It partially independent because of the LLVM, which we use to generate the code for the JIT templates and the code for virtual machine interpreter. It does not support all the platforms from out of the box. And we had to fine tune it to be able to generate the only all platform specific parts for our JIT and interpreter. It basically, answering your question, basically the JIT compiler is mostly platform independent. So, but we have to fine tune it to be able actually work it as expected.
Yeah. And so Alexander and his team have, lightly patched LLVM to be able to generate the code the way that we need it to be. And so those portions are going to be specific to the platform. But overall, it's like Alexander said, it is mostly platform independent.
Right.
Thank you, Alexander. Thank you, Seth. Next question here. What areas are you expecting to be highest growth for your tools?
Yeah, that's an excellent question. So, typically, historically speaking, we're very enterprise focused. If you look at our customer layout, we have, most everybody is in the enterprise space in some point. I think we have some very special technology to be able to run, dynamic language runtimes, which are traditionally, slower and more expensive, but we're able to run it sort of in these tighter, like right now we're running on the cloud, for example. We've been like Amazon's Graviton ARM processors. We've been running up there, and you're going to be paying cost on memory, and how much time it's using up. And so it's very important to have sort of a trim profile in those spaces. And so that's something we really think we can make very special with our product. We can get down pretty trim if we really want, to put the time to do it. And that's sort of what we are doing. And so we're just getting better and better at it. And so I'm very excited to see the future in the cloud and sort of the IoT space.
Thanks, Seth. Next question here. How is it different when we compare JIT compiler and different technologies, for example, Android or Java?
Alexander, do you have any ideas on that? Maybe I need how is it different when we compare JIT compilers in different
Yeah, I want to clarify the question, so I make sure that I understand it completely.
Okay, no worries. If you could clarify your question a little bit, Savani, that would be great. We'll move on to the next question for now, and hopefully we can get a little more clarification. But the next question is, can you comment on your experience trying to apply this into sensitive real-time controls applications? If not direct, have you seen interest in a faster development platform, but still migrate to compiled code and final instantiation?
Yeah, well, I would say that, we haven't spent much time down at that level. I mean, we typically are running on, I think the trimmest so far we've sort of run on is a Raspberry Pi Zero. And the product runs nicely on it. Back in the day, actually, the Visual Age folks, or really OTI, the folks that built the virtual machine technology, actually generated, all this. So in Smalltalk, there was this portable assembly all in Smalltalk, and it generated code for all these processors that were all these embedded, really tiny things that were in microwave ovens, things of that nature. It wasn't a runtime necessarily, a big runtime on top of it. And the VM has always been set up to sort of remove large pieces of it, like the file system. That doesn't have to be part of what we build, or other things like that. So to answer your question, we personally these days haven't spent much time there. I think we're actually trying to find, so I know that we've sort of looked into grabbing some of these lower level boards and start playing with them and seeing what we can do, because the last part of your question there, I think is really important, which is, yes, I think a faster development platform, on that level, is something that we may be able to bring our skills to. I think that's true. I hope that answered the question.
Thank you. Oh, here's the additional context from Sabani. And Bobby said, yes, you did answer his question, so thanks,
Okay.
Seth. So JIT compiler is a component of the Java runtime environment and improves the performance of the Java apps at runtime. When we compare the performance to Android JIT Java, how different is an IoT JIT?
Answering this question, I don't see any fundamental difference. So it generates, Java generates the code at runtime, and VAST platform generates the code at runtime. So it works in a similar way, but the only difference that we use template, it's a template JIT technique, and Java used profile guided and tracing. It's the mix of the techniques they use. So
yeah, and I would think that for the Android, for mobile and that kind of stuff, they're probably, and I haven't looked, honestly at their implementations, but I would guess, there's got to be a substantial effort to get that memory footprint down, and make some other trade-offs with regards to raw performance, just because, and energy efficiency as well. Kind of everything we were pointing out. I imagine they've dealt with that because they got to run on these little mobile phones. So yeah.
Thanks, Alexander. Thanks, Seth. Just getting a lot of positive feedback here. Steven says, thanks for this. As a Java EE architect and dev in a past and future life, I was obsessed with JVM performance, but worried more about GC. This was an eye-opener, especially more modern implementations in other languages. So,
that's good to hear. So when I was on Alexander's team, Alexander and those guys, that was sort of the memory manager was what I basically was responsible for. So we have a generational garbage collector, and basically you're right. I mean, so it's a mark and sweep. It's a compactor. So think of like disk, for those that don't know, think of disk defrag on Windows. It's kind of doing that in some segment of the heap, but there's another section where it runs a bit faster. But at the end of the day, that is a consideration. You want to get it down to, I mean, I think ours typically runs about 3% of the total usage, but still, I mean, it's definitely more expensive than allocating and keeping track of your own memory, which is why I like, I think languages like Rust are interesting when I've used those, because you kind of, you're kind of working with that trade-off, I guess, a little bit. It's a little bit more upfront for you to consider, but it still helps.
Thanks so much, Seth. Great presentation. I just want to point out that there are 4 Instantiations employees here, including Seth, the president and CEO, but they're almost all in different countries except for Greg and Seth. So thanks for joining us. Really cool.
Pleasure.
You guys here. Another question. Hey, Greg. What were techniques or algorithms used for JIT complier implementations?
Oh,
Alexander, do you have a thought?
I already mentioned that we are using LLVM, and we use LLVM at intermediate level as so-called LLVM IR. We use it to produce both the interpreter codes and the templates for JIT code, and so
and the template part was really important. I think we have, if I'm not mistaken, some experiments where we dragged in the LLVM static compiler pipeline in memory, and if you can even go look it up. I mean, that it's huge and it's slow.
Right. So we tried to use LLVM to compile the method as it is, but LLVM is not quite suitable for the first tier JIT, and because it's quite slow, even if we omit the most of the optimizing passes which LLVM provides. So we are considering it as a second tier JIT we will probably implement in the future. But the footprint of the binaries which LLVM has is quite big for IoT, and probably it will be optional.
Good, yeah.
Thanks so much, Alexander. Wonderful presentation, guys. I just want to remind everybody that this is being recorded, so it will be posted to Riot's YouTube channel. We do have another question here from Tom. You mentioned earlier in the talk moving to additional platforms beyond Windows and Linux. It seems that use cases at the edge will greatly increase for JIT compilers. What is your roadmap? What is on your roadmap for new platforms or features to capture the IoT edge opportunity?
Yeah, great question. So yeah, the first stage was that we needed ARM support, which is kind of something we've tackled. Well, it's been in the works for a couple of years, but we really we needed the speed. Like we built this, we have a C interpreter that allows us to port to basically any platform in just, a couple of weeks. It's not hard. In fact, the ARM port took just a few hours actually to get it going. We also, all the pieces, we make use of a lot of external technology. But we really needed to get the ARM story going. And so far, we already had Linux support. So the story has been, Linux, ARM-based systems. Mostly we use the Raspberry Pi, but as I said, I mean, we also are running on Amazon's Graviton 2 processor up in the cloud. But I think as we move forward, I mean, we're trying to get a sense, okay, how much interest is there in sort of what we've built for the IoT space? And if there is, the interest is there, I think we'll continue and start to get a better sense of, okay, well, where else can we bring this platform of ours? So I think there's still some unanswered questions with regard to how much further, you know, how deep we can go in the IoT community. But as I said, I mean, I think there's really some special opportunities for us in particular.
Again, thank you, Seth Berman. Thank you, Alexander Mitin. Really great to have you guys here today. And up next, we have Mariano Martinez-Peck, who will be also with Instantiations. So we're super excited to have back-to-back Instantiation sessions here today. Just a great organization. Very thankful to have them in our sponsor lineup. Thanks again, Seth. Thanks, Alexander.
Thank you. Appreciate it.